Hello all. I tried to film this yesterday, but I ran out of time because I had to do something else. So I hope this doesn't come too late because this is a Unit 2 paper and I believe that the exam is tomorrow. So hopefully you will have some time to look into the video. If not, you will watch it and it might be helpful for the November exams. This is from October 2025 and it's a Unit 2A. And from what I was told, these are afternoon papers that they are taken by students who cannot take the morning papers. So something like that. Anyway, let's dive in. So question 1, the equation I equals nqvA relates the current in a sample of material to the movement of free charge carriers in the sample. Which of the following is a correct definition of one of the terms in this equation? So n represents the number of charge carriers in the sample. That's wrong, actually. It represents the number of charge carriers per volume in the sample. So q represents the total charge stored in the sample. That's wrong. That's the charge of the charge carrier. So in most cases, that's an electron. So the charge is 1e. And then v represents the drift velocity of the charge carriers in the sample. That's actually correct. So that's our answer. And then a represents the surface area of the sample. That's wrong. It actually represents the cross-sectional area of the sample. Okay, so if it's a cylinder, for example, the cross-sectional area will be this circle that I marked with, that I drew with black. Okay, so let's move on to the second question. The equation n, where n is an integer here, times lambda equals d sine theta can be used to determine the wavelength of laser light that has passed through a diffraction grating. Which of the following is represented by d in the equation? So it's of course the spacing between the grating, the consecutive lines in the grating. So let's find the right answer. Option A says it's the distance between adjacent lines on the diffraction grating, which is actually the correct answer. B, the distance between the diffraction grating and the screen. No. C is the number of lines per meter on the diffraction grating. That's actually 1 over d. Okay. And then D, the order of the maximum observed on the screen. That's n. Okay, so let's move on. Question 3. The graph shows the current voltage characteristic for a filament lamp. Choose the graph that best shows how the resistance R of the lamp changes with temperature. So this is interesting because I is 1 over R times V. So the gradient of the IV curve is actually 1 over R. So if you notice, the gradient is the tangent to this line. So the gradient actually decreases, which means that 1 over R decreases as V increases, okay? Which means that actually R increases as V increases. But notice that as V increases, as the voltage increases, the temperature in the filament lamp increases. So this tells us that the resistance actually increases with temperature. So the correct answers are either C or D. Which one do you think is the correct answer? Pause the video and write in the comments, and then I will just tell you the answer. So, I mean, if you're back from the pause, the correct answer is actually C. Okay, and the reason is that R is not 0 if temperature is 0. Okay, so C is the correct answer. And again, you have to be careful with the gradient because here the gradient is 1 over R. So 1 over R decreases as V increases, which means that R actually increases as the voltage increases. And an increase in voltage, again, means an increase in temperature. Okay, moving on. Okay, question 4. I had to stare at this for a while to figure out the correct answer because it gave me a lot of confusion, I have to admit. So a sound wave travels through air. The diagram represents the displacement of air particles along the wave at an instant in time. There is a compression at position V. at which position is there a rarefaction. So if there is a compression at V, it means that immediately to the right of V, the particles move to the left, okay? So if you continue this wave like that, it means that to the left of the position V, the particles move to the right, okay? And this doesn't make any sense because usually if the displacement is positive, we mean that particles move to the right and not to the left as we draw here. So the only way this makes sense is that we have a wave that travels to the left actually, okay? So I hope this makes sense. If it doesn't, let me know. So if that's the case, then if we go to Z, okay, Z is also a compression because immediately to the right of Z, particles move to the left, okay? So they move towards Z, and immediately to the left of Z, particles move to the right, okay? So you get a compression, okay? So the only candidate for a rarefaction is X, because W is a particle that moves to the left with maximum amplitude, and X is a particle that moves to the right with maximum amplitude. So if we move to X, we will see that, let me think again. So yes, a particle immediately to the right of X moves to the right, and immediately to the left of X, it moves to the left. So all particles move away from X, and we get a rarefaction. So the correct answer is actually X. So option B. Okay, so this was a tricky problem. So if my explanation didn't make sense, let me know. Why did this move down there? I don't know. Can we move it up there? Okay, I don't know why that happened. So anyway, this was question number 4. Let's move on to question number 5. Okay, question number 5. Solar panels are devices that use sunlight as a source of energy to generate electricity. A solar panel has a surface area of 1.54 square meters. The intensity of radiation incident on the Earth's surface is 1050 watts per square meter. The manufacturer states that the maximum output power of the solar panel is 250 watts. Which of the following could be used, to calculate the maximum efficiency of the solar panel? So if we write efficiency as useful output over input, we can immediately read the information given as follows. 250 watts is the maximum output power, okay? So that's our useful output. And then what's the input? We have a surface area of 1.54 square meters, and the intensity of radiation is 1050 watts per square meters. So if we multiply these two, we get the input wattage, right? So 1050 times 1.54, and this will be watts, which cancel because efficiency is a number, okay, it doesn't have dimensions. And we can immediately read the correct answer as, which one is it? D. Okay, let's move on to question number 6. A small metal cube with sides of length x is connected in a circuit. The current through the cube between opposite faces is I, and the potential difference across the cube is V. Which of the following gives the resistivity of the metal? So if we make a small drawing, it will help here. So what they tell us is that we have this cube, okay, with side x, all right, and we apply a voltage there, okay, so you have a voltage. Maybe a better drawing would be this, okay, so this is the voltage, okay. Now the resistance is given by Ohm's law, okay, V over I, but also we know that the resistance is given by the resistivity times the length of the resistance over its cross-sectional area, okay? So let's combine all these to get rho times the length of this cube is x, and its surface area is x squared, right? And this will be equal to V over I. So one of the x's cancel, and the resistivity can be written as the voltage over the current times x, okay? which is option A. I hope this makes sense. In this test, I forgot to comment on some common sense ways to find solutions to problems. So in this case, for example, let me think, is there anything you can eliminate? B has the wrong dimensions. C has the wrong dimensions. Actually, B, C, and D are totally wrong just by inspection, because you need, if you write the formulas down, you will see that resistivity has dimensions of voltage over current times some length. Okay, so this is wrong, and this is wrong immediately without even knowing, without even going through the trouble of finding the correct answer. So let's do question 7. Two waves, each with a wavelength of 2 centimeters, leave a single source in phase and follow the paths shown. So let me use two colors. So we have the first wave that travels in this direction, and then the second wave travels in this direction. Okay, so there is a path difference. Which of the following is the phase difference in radians between the two waves as they meet at point A? Okay, so in general, the phase difference is given by 2 pi over lambda times delta x. And I remember I checked before. Let's go to the back of the paper. I think this is one of the formulas that you actually have to remember because they don't give it to you. Let's see, you need to, yeah, unfortunately they don't provide you with this formula, so you need to remember it. But I'm going to show you two ways to solve this problem anyway. So, okay, if we just plug in numbers, we have 2 pi over lambda, which is 2 centimeters, times delta x. What's delta x? Delta x is 4 plus 4 is 8. Maybe let me write it like that. So 2 times 4 minus 2 times 2.5, so 3 centimeters, right? So this is the answer. So we get 3 pi. And don't panic, because 3 pi is the same as pi, okay? So C is the correct answer here. But maybe that will lead you to confusion. So another way to see the path difference, the phase difference in this problem, to find it, you can immediately realize from delta x. So delta x is 3 centimeters, which is equal to lambda, which is 2, plus lambda over 2, which is 1. Okay, so delta phi, whatever, is going to be equal to pi, okay, because lambda gives you a phase difference of 0. Okay, so that's another way to think about it. So yeah, there is nothing else to say here. And again, this is a problem you can again solve by inspection, because the path difference is a multiple of lambda, okay, and lambda over 2. So pi over 4 cannot be the correct answer, pi over 2 cannot be the correct answer, and 3 pi over 2 cannot be the correct answer, because you need an integer multiple of pi when you're dealing with path differences that are multiples of lambda or lambda over 2. Okay, I hope this makes sense. Let's move on. Question 8, the temperature of thermistor is increased. Which of the following has the greatest impact on the resistance of the thermistor when the temperature is increased? So you get increased kinetic energy of conduction, electrons. That's not correct. Increased lattice vibrations. That's not the case with thermistors, because thermistors are made of semiconducting materials. So maybe I have to write this down. Semiconducting materials. So these materials have the property that when you heat them up, you get the electrons in the conduction band of these materials. So the resistance drops, okay? Whereas lattice vibrations are more relevant to metals, okay? So option C, increased number of collisions between conduction electrons and atoms. No. And then D, increased number of conduction electrons, which is what I just said about semiconducting materials in general, okay? So the same happens with solar panels, for example. As you increase the temperature, the resistance decreases, okay? So 9. Two polarizing filters X and Y are arranged between a light source and an observer as shown. The intensity of light reaching the observer is a maximum. The observer rotates filter X, the observer then rotates filter Y, so that the intensity of light is a maximum again. Which row of the table shows possible angles of rotation for the filters? By the way, this is a typo. It should be X and Y. Don't know why it says header. I guess that was a placeholder word that they meant to change later and they forgot. But anyway, it should be X and Y. So we will work with the process of elimination here. So in option A, you immediately see that these two guys are actually perpendicular to each other because the 180 minus 90 gives you 90 degrees. Okay, so they are perpendicular to each other. So the intensity will be 0 with option A. Same goes with option B, because 270 minus 180 is also 90. So that's wrong. And then C, you get 270 minus 90. This is a difference of 180. So that works actually. So C is the correct answer. And then in D, you see that 360 minus 270 is 90. Okay, so that doesn't work because the filters will be perpendicular to each other, meaning that the intensity will be 0 after the second filter, filter Y. Okay, so option C is the only one that works. Moving on. Question 10, light of wavelength lambda traveling at speed c, that was not necessary. I mean, light does travel with the speed of light. I don't know why they mentioned that. Okay, is incident on a metal surface. Photoelectrons are emitted from the surface with a maximum kinetic energy 1/2 mv max squared. The graph shows the relationship between 1 over lambda and 1/2 mv max squared. Which of the following shows how the gradient of the graph can be used to determine the Planck constant h? So let's write the photoelectric equation, which is, I think this one is actually given, right? You don't have to remember it. Let me see. Okay. By the way, I'm a strange kind of person, teacher, professor, I don't know, PhD, whatever you want to call me. In that, you know how they tell you don't memorize things in physics? I'm actually against that. I think it's good to memorize things because you see how, okay, let's assume that I didn't remember the formula. I will have to turn to the back of the paper, find the formula and copy it. So I would lose 30 seconds, okay? This paper has 20 questions, okay? About 20 questions, say. So if I lose 30 seconds per problem, let's make it a minute. No, 30 seconds, okay. So 30 seconds per problem means in the total of the paper, I will lose 10 minutes just because I don't remember the formula. So it's good to remember things, okay? And also, okay, I don't mean as remembering these equations in a dry form. Okay, you have to know the meaning of them, but it's good to remember them. Okay, I hope this makes sense. Let's go back to the paper. All right, so the photoelectric equation is h times frequency is equal to the work function plus 1/2 mv squared, mv max squared. Okay, so we can write this as hc over lambda, okay, equal to phi plus 1/2 mv max squared, okay, and then we can write that 1 over lambda is 1 over hc times the work function plus 1 over hc times 1/2 mv max squared. And this has the form y equals to c, okay? So this will be our constant plus m times x. So this will be x, okay? And this will be m. So m is the gradient, of course. So the gradient is 1 over hc. So h is 1 over c times the gradient, which is option B, okay? Hope this makes sense. This was section A. Not too bad. I think the previous unit 2 I uploaded was harder, but let me know what you think. So let's move on to the second part, section B. Okay, question 11. It awards 4 marks, which is another thing I forgot to address in this paper. So in general, my rule of thumb is that you guys have to spend about a minute per mark, if that makes sense. So this problem awards 4 marks. You should estimate that it should take about 4 minutes. Okay, if it takes you 6 minutes, it's not the end of the world, but you know, it's good to have timing in your head so you don't run out of time and you get as much marks as possible from a paper. And okay, the other thing that I say about papers is that you have to kind of let go, meaning that if you start working on a problem and you cannot immediately infer what you have to do, or if you don't know what to do, and so on, skip it. Don't waste your time trying to think about it because you're gonna panic. And then if you panic, you're gonna give up, etc. So don't panic, skip it, move to the next problem that you actually know how to solve all the problems that you actually know how to deal with, and return to the problem that you didn't know what to do with in the end. Okay, don't waste time. Time is money. So problem 11. The diagram shows some of the energy levels for hydrogen. Okay, identify the transition which would result in the emission of light of wavelength 660 nanometers. So, okay, so the energy difference would be equal to h times the frequency. Okay, I mean, if I get a transition from, I don't know, from this level to this level, I think that's the answer actually. I did it instinctively though, okay? So if an electron jumps from the minus 1.51 electron volts energy level to the minus 3.39 electron volts energy level, a photon with energy hf will be emitted. Hf is equal to hc over lambda. So in our case, lambda is 660, so let's write down Planck's constant. Okay, and this is joules times seconds. C is 3 times 10 to the 8, and that's meters per second. And the lambda is 660 times 10 to the negative 9 meters. So meters cancel, seconds cancel, and of course, this is given in joules. So 3.01 times 10 to the negative 19 joules, and we have to divide by 1.6 times 10 to the negative 19 joules times electron volts to minus 1, and this will give us 1.88 electron volts. And okay, the only transition that works is from minus 151 electron volts to minus 3.39 electron volts, which is exactly 1.88 electron volts. Okay, so this was question 11. Let's move on to the next one. Question 12. Sensors can be fitted to the rear bumper of a car to help the driver reverse the car safely. The sensors emit ultrasound pulses that hit an object behind the car are reflected back to the sensors. The time taken for the reflected pulse to return is measured so that the distance to the object can be determined. State why it is necessary to emit the ultrasound pulses. So let's use a clean page. So this is question 12, okay? And problem A. All right, so the pulse must return to the sensor before the next one is emitted, okay? Otherwise, you cannot tell which reflected pulse belongs to which emitted pulse. Okay, and that's the answer. I mean, it's more than enough, I think. So let's do part B. A car manufacturer claims that the sensors are able to detect objects from a distance of 0.1 meters from the car. Calculate the maximum duration of each pulse, and they give you the speed of sound in air, which is 340 meters per second. So let's do B. The distance they cover is equal to the speed of sound times the time over 2, because remember the pulse has to go back and forth. Okay, so they don't have it here. So I mean, if this is the car and this is a wall, the emitted pulse has to travel back and then come uh, back and forth, right? So it gets detected. We are interested in the time the pulse takes. So time is 2 times the distance over the speed of sound. So that's 0.2 over 340, which yields 5.88 times 10 to the negative 4 seconds. Very short pulse, okay? Part C, suggest why the sensors may not help the driver when reversing towards an ascending ramp. Okay, so let's see what's going to happen. The sensors are down here, right? I mean, you see that they are in the bottom of the car. So let's say I send a pulse. What's going to happen? It's going to bounce off that way, right? It's not going to come back. Okay, so that's the answer pretty much. So it bounces off in an unknown direction, so it's not going to help. Of course, the car is not going to crash in that case because, I mean, it's a ramp, right? So, CI, the ramp deflects the ultrasound away at an angle, so it does not reflect straight back to the sensor. Okay. Part 2 suggests why the sensors may not help the driver when reversing towards a thin post. So let's say you have a thin post. So again, the problem is the same. I mean, it might not see it. I mean, the pulse might not hit the post. Okay, so that's the problem. So let's write it down. The post is too thin to reflect enough ultrasound back to the sensor to detect it. And by the way, I didn't know that ultrasounds are used for this. I was expecting some sort of light or microwaves or something like that. So I wasn't aware that they use ultrasound. Let me know if this is the case. I actually don't know. I'm not big into cars. I mean, I like cars, but I don't care that much. So yeah, I mean, it was a surprising question for me. You know, you learn new things as you grow older, guys. So, okay, question 13. The refractive index of glass varies with the color of light. The refractive index of glass for red light is 1.513. The refractive index of glass for violet is 1.532. A ray of white light is incident on side AB of a rectangular glass block as shown. The red light and violet light from the incident ray arrive at slightly different points on side CD. Determine the distance between these points. Okay, so let's do some math. So let's use a clean page. So n sine 54 degrees, right, is going to be equal to the index of refraction of red light times sine of the angle for the red light. Okay, so sine, and this one, it's r, so sine of theta r is 0.81 over 1.513. So theta r is 32.32 degrees. We will do the same with violet light. So we will have 0.81 over 1.532. Okay, I hope it's clear. I did it a little bit fast. So theta for violet light is 31.92 degrees. So if we go back here, we see that the red light, actually let's use red. Okay, so the red light will be, say, this one, and then the violet light. Do they have violet here? Is this considered violet? Maybe. So the violet will be that one. Okay, so we know this angle, and we also know this angle. Okay, so let's call this XR, and let's call this distance, this one, XV. Okay, so from the geometry of the problem, we see that the tangent of theta violet is going to be x violet over 6.4 centimeters, which is this side, right? So x violet is going to be 3.99 centimeters. And I'm going to go to the back of the paper and copy this result actually first. So x of the violet will be 3.99 centimeters. And then for red, we will have x red equal to 6.4 times tangent of theta red, which gives 4.05 centimeters. Okay, so delta x, let's use black. So delta x is going to be simply the subtraction of those two. So 0.06 centimeters will be the spacing between the two rays. Okay, this was A, part A. Okay, part B. White light is incident on a boundary between glass and air as shown. Explain what happens to the red light and the violet light when meeting the boundary. Your answer should include calculations. So let's do the calculations. So let's do B. So we have the index of refraction of red times sine of 41 will be sine theta r times the index of refraction of air, which is 1. So sine of theta r is 0.66 times the index of refraction of red, which yields 0.99, which means that theta r is 83.03 degrees, quite large. Okay. Now for violet, and violet, sine of 41 is sine of theta violet. So if we do the calculations, we will find that sine of theta violet is 1.01, which is larger than 1, which means what? It means we get total internal reflection. So total internal reflection for violet. Okay, so if we draw the lines, we will have red flying off in this direction, maybe here. Okay, so that will be 83.03 degrees. Excuse me. And then for violet, we will get this reflection. Okay, and this will be 41 degrees. All right, so this was question 13. Let's move on to the next question. Okay, question 14. A student connected the circuit shown the battery has negligible internal resistance. Okay, the graph shows how the resistance of the thermistor varies with temperature. Again, the thermistor, okay. The reading on the voltmeter is 3.42 volts. Determine the temperature of the thermistor. Okay, let's again create a clean page. So by the way, the A version of these papers, like Unit 2A, Unit 3A, etc., they don't provide space for you to write. They actually do, but in the back of the paper. So I don't know why they do that, but anyway, that's why I use clean pages. So resistance is voltage per current, right? So current is voltage over resistance. What's the voltage again? Wait, I'm confused. Yeah, 3.42, and the resistance is 11.5. So let's use that information to find the current. 3.42 over 11.5. So that's 0.3 amps. So the voltage of the thermistor is then 9 minus 3.42, which is 5.58 volts, which means that the resistance of the thermistor is equal to the V of the thermistor over the current. So 5.58 over 0.3, which yields 18.6 ohms. And if we go to the graph, we see that 18 is somewhere here. So this is 18. So that's about 34, 35 degrees, something like that. So the temperature of the thermistor is about 34 degrees from graph. Okay. B. The student suggests that if the EMF of the battery is doubled, the reading on the voltmeter, will double. Assess whether the student's suggestion is correct. Okay, it kind of makes sense, but let's see. So, doubling EMF increases the current, the current which causes the thermistor to heat up. Okay, so that's the first effect. So as temperature rises, the thermistor decreases, the thermistor resistance decreases. Okay, so the resistance of the thermistor decreases. This means the thermistor takes a smaller share of the total potential difference than before. Okay, so the voltmeter reading will more than double. So student is wrong. Okay, I hope this makes sense. So pretty much we will have the resistance of the thermistor decreasing, which means that the voltage across the thermistor will decrease. Okay, and therefore the voltage across the resistance will increase more than twice than what it was before. Okay. Okay, question 15 has a star, which means that's a long writing problem. My least favorites, I have to admit. Okay, I like doing calculations more than explaining things like that. So anyway, the images show some toy glow-in-the-dark stones. I'm not aware of this thing. I don't know. It sounds like something they would have in Japan for some reason. But you guys let me know in the comments. So I've never seen this before. Okay. After being exposed to sunlight, the stones glow, emitting light. I guess this is the picture over here, the second picture. Okay. The packaging states that the stones work with any light source. A student tests this by illuminating the stones with light from a red laser, a green laser, and a violet laser in turn. The red and green lasers have no effect on the stones, but the glow is seen immediately when the violet laser is shown on the stones. The light produced by the lasers has the following wavelengths. Red is 650 nanometers, green is 530, and violet is 405 nanometers. Suggest how these observations could be explained by the photon nature of light, but not the wave nature of light. So they kind of prompt you to say things related to the atomic nature of matter. So let's start writing explanations. So electrons in atoms. By the way, in long writing problems such as this, where 6 marks are awarded, you generally have to write six sentences. So between 5 and 7, something like that, will give you the full points. Okay, so electrons in atoms of the stones, electrons in the atoms of these stones. Okay, excuse me, have fixed discrete energy levels. Okay, for an electron to jump to a higher energy level, it needs a photon with exactly the right energy. Okay, photon energy, excuse me, is given by energy is equal to h times the frequency. So frequency and color determines whether a certain color will work. Okay, each photon can interact with only one electron at a time. Okay, violet photons have exactly the right energy to match the gap between two energy levels in the material. Okay, so red and green photons have the wrong energy, so nothing happens. Okay, so under the wave model, energy will build up, okay, gradually. So any color would eventually work. Oops, I don't know why I did that again. Would eventually work, which is not the case. Okay, this was a long answer, but I hope it makes sense. So this was question 15. Let's move on to the next one, which is question 16. Okay, a student set up the circuit shown to determine the EMF E and internal resistance R of a cell. I is the current in the circuit and R is the resistance of the variable resistor. Show that for this circuit, R is equal to the EMF over I minus R. So let's use a clean page again. So this is problem A. So the total resistance is simply R plus lowercase r, the internal resistance. So the EMF is I times R total. So that's I times R plus R. Okay. So E over I is R plus R. So we can write that R is the EMF over I minus R. Okay. Which is what they ask to prove. B. The student varied R and measured corresponding values of I. The student then plotted a graph of R against 1 over I as shown, so we get a straight line. Determine E, the EMF, and R, the internal resistance for the cell. Okay, first of all, let's observe that this formula over here has the form Y equals mx plus C. So C is minus R, and m, which is the gradient, is equal to the EMF, right? Yes. Okay, so let's go back here and immediately write that minus R is equal to minus 2 ohms. So R is 2 ohms. I mean, you can see it over there. Okay, and now for the gradient, I'm gonna choose this point and this point. Any 2 points will work, but anyway, we need this delta R and we need this delta 1 over I to calculate the gradient, and the gradient is the EMF. So the gradient is delta R over delta 1 over I. So 10 minus 4 over 8 minus 4. So 3 over 2, which is 1.5 volts, which is equal to the EMF. Okay, so that's the answer. And there's a part C and a part D. Okay, in part C, they say the student adjusts the variable resistor so that R increases. Explain how this will affect the power dissipated by the internal resistor. So let's actually write this down over here. So increasing R raises R total. So current drops. Okay. Since power is I squared times the internal resistance, the what's there right there? So since the power is I squared times R, the power dissipated drops. Okay, so this is what's gonna happen. Okay, D, they added a second identical cell in series with the first cell and repeated the experiment. Add a line to the graph to show the results of this experiment. Okay, so I guess just adding to this line does the trick. So if we add a second cell over here with the same EMF and the same R, then the internal resistance will be minus 4. So I'm going to draw this with, let's do red. So the graph will start there and the slope will be 3. So it will be twice this one. So maybe something like this. Is this twice that? We can actually write that gradient will be 3. Okay, so this is what's going to happen. And this was question 16. Let's move on to the next one, which is question 17. Okay, question 17. The photograph shows the Golden Gate Bridge in San Francisco, USA. I still regret that I haven't visited while living in the United States. Such a shame. I've never been to California, actually. Anyway, the bridge has two main cables. Attached to these cables are smaller suspending cables which support the road. Okay. Wind causes each suspending cable to oscillate, so standing waves form on the suspending cables. Question A, explain how a standing wave can form on a cable that is fixed at both ends. Okay, let's create a clean page. So wind drives waves along the cable, which reflect off both fixed ends. Okay, the reflected waves superpose with the incoming waves. Okay, where destructive interference occurs, sorry for my spelling, interference occurs, you get a node, and where constructive interference occurs, you get an antinode, right? You get an antinode. Sorry, I blanked for a second. So this, forming a standing wave. Okay. B. The diagram shows a standing wave on a cable that is fixed at both ends. X and Y are 2 points on the cable. Describe the motion of points X and Y on the cable. So X is an antinode and Y is a node pretty much. So let's write this down. So B, X is an antinode. So it oscillates with maximum amplitude, with maximum amplitude varying between a maximum and 0. Okay, now Y is pretty much stationary. So Y is a node, so it's stationary with 0 displacement. All right. Okay, this was problem B. C. In strong winds, the Golden Gate Bridge emits a humming sound. One of the suspending cables on the bridge has a mass of 2.1 times 10 to the third kilograms and a length of 87 meters. Show that the mass per unit length mu of the cable is about 24 kilograms per meter. Okay, this one is easy. So C1, we get that mu is 2.1 times 10 to the third kilograms. The length is 87 meters, so this yields 24.14 kilograms meters to the minus 1, which is about 24 kilograms meters to the minus 1. Okay, part 2. The lowest frequency of the humming sound produced by the bridge is 280 hertz. The total mass of the road on the bridge is 140 times 10 to the 6 kilograms. The weight of the road is supported equally by 500 suspending cables. The range of lengths of the suspending cables is from 3.5 meters to 160 meters. The value of mu is 24 kilograms per meter. Deduce whether the lowest frequency standing waves on the suspending cables could be producing the humming sound. Okay, so this is a little bit complicated. So let's start from the fact that the velocity of a standing wave, of a wave in a string, is equal to the square root of the tension over the mass per unit length. But the velocity is lambda times the frequency, and this will be equal to the tension. The tension is caused, by the mass of the rod times G, over 500 though, okay, because this mass is distributed over all the cables, which are 500, times nu, okay? So lambda for this lowest frequency wave will be 1 over f times the square root of mg over 500 nu. And if we plug in numbers, we find 1 over 280, the square root of 140 times 10 to the 6 times 9.81 over 500 times 24. And this yields exactly 1.2 meters for lambda. The lowest possible lambda is equal to 7 meters, which is 2 times 3.5 meters, which is the shortest cable. So, no, the humming sound is not due to the cables. Okay, this is a little bit complicated, but I hope it makes sense. So I don't know why I wrote 2 twice there. So this was question 17, guys. And let's move on to the next one. 18 is the last one in this paper. Okay, 4 identical resistors A, B, C, and D are placed in a circuit as shown. Determine the power dissipated in each of the resistors. The resistance of each resistor is 2 ohms. So, okay, let's use a clean page first. So this is part A. So 1 over R of the section B, C, D is equal to 1 over R, B plus R, C plus 1 over R, D. I hope this makes sense. I'm talking about this section over here. So these two add up, but then BC, the combination BC together is parallel with D. That's why I wrote all this thing here. So 1 over R, B, C, D is 1 over 4 plus 1 over 2, which is 3 over 4. So R, B, C, D is 4 over 3 ohms. Okay, so the R total is then 2 from A, right? Plus 4 over 3, which is 1.33. So 3.33 ohms is the total resistance in this circuit. So the current is voltage over R total. So 10 over 3.33. So 3 amps is the voltage, the current in this circuit. So for A, the power across A is going to be I squared times RA. So 9 times 2, so 18 watts. That's the easy one. Okay. Now the voltage across A is going to be I times RA, which is 3 times 2, 6 volts. Okay. So the voltage across BC is going to be equal to the voltage across D. Okay. So let me erase a few things here because I created a mess. Okay, so that's going to be VA. And then we will have the voltage across BC. So this voltage will be equal to the voltage across D because these guys are in parallel. Okay, so VBC is going to be equal to VD and it's going to be equal to 4 volts because these two have to add up to 10 volts. Okay, so now we are in a position to find the currents across these combinations. So I across D is equal to VD over R, which is 4 over 2, which is 2 amps. So the power dissipated across D is going to be I squared D, okay, times R, so 8 watts. And now the current across the combination BC is going to be equal to VBC over 4, because now this current passes through 2 resistances. So we have 4 over 4, which is 1 amps. So the power across B is equal to the power across C. So it's going to be I squared BC times R, so just 2 watts. Okay, notice that IBC plus ID is 3 amps, which is the current in the circuit, okay? Which makes sense because, let's erase again all this mess. So if we have a current I, which is 3 amps, here it will split into 2 currents, okay? So we'll have 1 amp here and 2 amps there, okay? So because of the conservation of current across junctions, pretty much, okay? So B, explain without further calculation what will happen to the power dissipated by resistor A if resistor D were disconnected from the circuit. Okay, so again, let's erase this. So if we remove this guy, we will have 3 resistors in series, okay? Which means that the total resistance will increase, okay? Actually, our total will be 6 ohms. I know they didn't ask us to calculate it, but the total resistance before was 1.33 pretty much, right? Sorry, 3.33. Now it's 6, okay? So removing D increases our total. So current through A decreases, okay? And since power is I squared times R, power decreases, okay? That's the answer. So part C, if the resistors in the circuit used in A were replaced with filament lamps, the resistance of each lamp will be different depending on the potential difference across it. Explain in terms of particles why the resistance of a filament lamp increases as the potential difference across the filament increases. So higher potential difference means higher current, okay, through the filament, okay. Greater current causes temperature to rise, okay. If temperature increases, the ions in the lattice vibrate more vigorously, okay. So electrons collide with the lattice more frequently, okay. So the resistance increases, okay. This was part C. This was unit 2A, excuse me, from October 2025. Let me know if it's useful. I'm gonna cut the video immediately and edit it and upload it because you guys need it for tomorrow, I guess. So this is it. See you in the next video. Bye.